Bead lies on a frictionless tube of radius L and rotates around it a vertical diameter with constant angular velocity omega. The question asks us to calculate this angular velocity. I took this question from MIT X's kinematics and dynamics course on EX. Okay, so I've drawn a little diagram here to help represent what's going on. So over here is the bead that we're concerned with. And what we want to make sure that this bead does is basically stay in the same position, same X position, same Y position. This is the radius of the hoop, L, and it's an angle theta to the vertical diameter over here. It is rotating around this vertical diameter and has an upwards, basically upwards omega angular velocity, since it's rotating counterclockwise. And this in blue here is the hula hoop, the perfect circle, I know. I've also drawn a 3D view to help demonstrate what's going on here. So the hula hoop essentially will be rotating this way. So I'm going to encapsulate the whole thing. That was horrible, my bad. And it's rotating this way. So the ball would be trying to go around, traversing around this path. However, we want the bead to stay in this position the whole time. Also, this is the radius L and the angle theta. Okay, so let us first construct a free body diagram to demonstrate what exactly are the forces that are acting. Okay, so this right here is the ball, and obviously downwards will be a weight force W, and this will be equal to mg. Also, there is going to be a force trying to pull it towards the center, the centripetal force, Fc. Now I can resolve Fc into its components, a horizontal component and a vertical component. Horizontal component acts this way, and if this is theta, this is Fc sine theta. And likewise, this will be Fc cos theta. Okay, now let's look at the unit vectors. So if I imagine this is my bowl, since the ball is ideally going to be spinning around, its unit vectors are going to be changing. At one point, there's going to be a unit vector pointing this way. However, when the ball's over here, it's going to be pointing this way, like polar coordinates. So we'll have basically a radial unit vector acting outwards, which we'll call r hat, one pointing tangential to the circular path, which I'll call theta hat, and one acting upwards, which I'll call k hat. However, as we see in this free body diagram, there is no theta hat forces. So we're not really concerned about this at all. We're just concerned about the k hat unit vector forces and r hat unit vector forces. So what are our k hat and r hat unit vector forces? So acting in the r hat direction, we've got Fc sine theta. And acting in the k hat direction, we've got Fc cos theta and mg. However, we don't want k hat to change at all, so we're going to set that equal to 0. In other words, Fc cos theta points upwards, so we have Fc cos theta, a positive version of that, minus mg is equal to 0 because there is no acceleration and it's in the same position. Or I could say that these two are equal to one another. Okay, what else we got? Well, we got a centripetal force acting towards the center. So acting towards the center here, which is this force over here, Fc sine theta. Fc sine theta, that will equal to, well, the centripetal acceleration times our mass, MAC. Now, what is AC? Let's remind ourselves that it's equal to negative omega squared r. Oh, I should also forgot to say that since this is the negative r hat direction, this will be negative. So let us substitute negative omega squared r into AC. We'll get that negative Fc sine theta is equal to mass negative omega squared r. Okay, now what we can do from the first equation, we can figure out what Fc is. So if I bring this down here, we get that FC, if I divide by cosine theta on both sides, is mg over cos theta, which I can now substitute over here. I'll get that negative FC, which is mg over cos theta, multiplied by sine theta, is equal to negative m omega squared r. However, we're not given r, so we cannot answer in terms of r. What is r? Okay, well, let's look back at this diagram over here. R will be the length of this sort of radius of this circular trajectory. Now, what is that? Well, if we know that if this is L and this is a right angled triangle, using basic trigonometry, we can figure out that this will be L sine theta, because it's the opposite over the hypotenuse will be sine theta. So L sine theta will be equal to the opposite length, which is R. Now I can substitute that in for R here, which is L sine theta. Now, also, I have not made this bit into tan theta because, as you see here, there's sine theta and sine theta here, which I could cancel out. But you could make it into tan theta and then divide by sine theta, get secant theta. But that's basically the same thing as 1 over cos theta, so it's not really going to make a difference. But you do you. I could also cancel out the m's and make both sides positive. So what I'm left with is g sine theta over cos theta is equal to omega squared L sine theta. Now I can cut out the sine thetas, and I can also divide by L on both sides to get omega squared is g over L cos theta. Now, what was the question? The question was to find out the angular velocity omega. So very simply, from this equation, all we got to do is take the root on both sides. And we finally get that omega is equal to root g over L cos theta.